but there is a test, I know, on a Thursday. Okay, those of you who are gone for Hope Song, I will extend that if you want. It just means you'll have to take it after Easter break. So you got to decide whether you want to take it out. It would be more advantageous for you to take it after Easter break or take it before. That's up to you. All you've really missed up to this point is a review on the Hess's Law. We spent a whole day reviewing that worksheet. And yesterday's lesson was mostly review outside of talking a little bit about entropy. Okay? You didn't miss much. That's good. Today is a bigger lesson. We are going to calculate entropy. What does that smell? Oh. Okay. So, notice how it says, first of all, for those of you who are gone, S is the symbol for entropy, and entropy is how disordered something is. Okay, but we also then talked about how if something's really disordered, doesn't mean it has no order, just has low order. Does that make sense, everybody? Okay? We are going to calculate your disorder or your entropy the same way we calculated change in H using this this equation. And this should make sense. If I'm trying to find the entropy of a reaction, I want to know how ordered the products are versus how ordered the reactants are. If I know how ordered the products and the reactants are, if I add them together, I should get the overall order of my new reaction. And where do you think we're going to find those numbers? On the chart. Everybody turn there. 344. We should have this out and handy and ready to go. We're not going to do this right at the moment, but we will in a sec. Okay? Units are a little bit different. Notice what the units are.
Joules per mole times Kelvin.
Okay? In enthalpy, it was kilojoules per mole. And the reason why it's kilojoules per mole is there's a lot of energy that can be stored up, and that's why we use kilo when we're doing heat stuff. The reason why we have temperature here is, didn't I just show you in problem number 3 of your homework that the temperature was important when figuring out the order of something? Why do I say that?
Because the fact.
Yeah, gases has higher energy. It's going to be more disordered than a solid. And we even compared two gases at different temperatures, and we said the one that has higher temperature is less ordered because it's more randomly moving. Okay? Sign conventions, it's really important. Let's quickly review. What does negative change in H tell you? Kind of, but from a exo or endo standpoint.
Exothermic reaction.
Exo releases, and this meant, just quick review because you're going to have now a different sign convention for entropy. And this should make sense, just like the negative meant released and the positive means absorbed overall. The positive means you are gaining disorder, isn't entropy disorder? So if you have a positive S, that means it's becoming more disordered. Okay? And a negative means your disorder is going down, or you could flip it and say you're becoming more
Stable.
ordered.
Orderly.
Okay? I don't want to use stable because that's more used for energy. I don't want to confuse those two things. Okay? You guys with me on sign convention? Okay? Let's do this problem. Find the change in your entropy. Now, I'm looking at this, and I can probably tell you right now whether I'm going to give a positive or negative. Can anybody do that? Just by looking at the equation? Are we going to get a positive S or a negative S? Any ideas?
Negative.
Really?
Why? If it's coming together, it's going to be what?
Oh.
What?
I'm going from very disordered gases
To a solid.
That's
to
not
a-
negative? Yeah, so more. It's more.
Oh, yeah, you're right. You're right. Woo! Woo! I flipped those. Look go. Everyone has those days. Everyone makes mistakes. All right. You guys are right. Mr. Kramer, you are wrong.
Tell them.
Where is
When she
that?
comes back.
Okay? Sorry. I butchered that one. Yes, it will be negative, and let's prove it. So. Yikes. That was one of my more bigger butchers of a mistake right there. Okay. So, products minus reactants, and if you look in your table, which column is the S values located?
The second.
The second column, okay?
Third, because the first one is called.
Okay, alright. So we got our product, okay? Coefficient is 1, so really it would just be 1 times that number. What is the number for NH4Cl?
94.6.
Joules per 1 mole degree Kelvin,
Oh,
right?
but then your answer will have a different unit because you both cancel. Okay. I was confused on the homework, like, but that is different. No, because they cancel
Yep,
out.
so you see that's my only product,
Yeah.
okay? And then I need to distribute my negative to both my reactants, correct? Okay, let's just start with this one. Again, I still have 1 mole.
192.8.
I'm trusting that these are the right numbers. Could we at least get someone to double check?
92.8,
Yep. Following? Am I going too fast? Okay. Now, I do say I'm adding, but remember this negative should get distributed to both, right? And I still have 1 mole here. Now, I know you're probably thinking, why are you even putting it in there, Mr. Kramer? Well, because so that you don't forget that when you do have coefficients, you still have to put those in there, right? And HCl is a gas. You can see it in here? 186.9. Okay, why don't you guys see if you, I want to make sure you guys can plug this in your calculator and get the correct number so you don't mess up the fact that this is negative. If you want to distribute it before you even plug it into your calculator, do it. Which means that that's a negative and that's a negative. You can really just do this. And that's how I would just plug it into my calculator. Just like that. And I wouldn't even have these brackets. These are gone. I've distributed my negative to both. Should be just like that. Why don't you guys solve quickly? Want to make sure we have enough time. It looks like we're slowly running out of time. So,
474.3.
474.3.
I got negative 285.1.
Yes!
Okay. I got a little scared there.
Well, I
Joules per mole.
Negative
Joules per
285.1.
Kelvin.
Joules per Kelvin, because the moles cancel, right?
Joules per Kelvin.
And you're going to see when I give you the Gibbs free energy equation why that Kelvin is there. Okay, those of you who got that wrong, did you figure it out after you redid it?
Yep.
Wait, what?
Calculated it.
Yep.
But
Well, actually, okay.
Everybody else, get that number.
User error.
What are we
Natalie,
doing?
did you get that?
What is my?
Okay, Tyler?
What are we doing?
Quinlan, you able to get that one now?
I keep thinking you put in. You just.
I accidentally minus it, so I added.
Yeah, well, so I distribute the negative. If you want to keep it how it is and then distribute it on your own, that's fine. Okay? Now, if like this was already a negative, then I would make it a positive. But, yep, all right. Now, the next problem, or actually, let's go back to this one, because it does say, does it increase or decrease the entropy? Okay, it decreases the entropy, which what does that mean?
There is more order.
More order. Okay? You might want to write that down next to it so that you have that along with it. Because on your test, you will probably be asked, is it exo, is it endo? Is the entropy increasing or decreasing? Is it ordered or disordered? You'll have to answer those questions. So the sign conventions for this particular stuff is more important than maybe you think. Okay? Because a negative number means something. The positive number means something. It's not just like math where they're just there for the fun of it. Okay. Quickly, if the entropy of a system increases, its order decreases. Because entropy means disordered. Okay, now we're not going to do this one for the sake of time. This is still asking you for find the change in S. You're going to use that equation, just like we just did. Does that make sense? The only difference about this equation and the previous equation is what?
They're 2 instead of.
That makes sense. Same process. Still products minus reactants. Still find the numbers in the chart. Yes? Doing it just like the previous problem. Just now we have coefficients. So can I just kind of just skip it and move on then?
Yeah.
Are you guys cool with that? I want to spend the remaining time talking about Mr. Gibb. Okay. What you are going to find out is that in chemistry, there's not one thing that's going to tell you everything you need to know. Okay? When I talked about earlier about that true or false question, and I said thermodynamically favorable, exo or endo, and exo was more favorable from an energy standpoint, that's not the only piece of the puzzle. Because what we talked about yesterday was an entropy law. Do you remember the entropy law yesterday, those of you who were here? What does the entropy law state? Yes, things that naturally go from order to disorder. So, there are really two factors. I want to know from an energy standpoint, is it favorable? But I also want to know from an entropy standpoint, is it favorable? Just like every chemical reaction has bonds breaking and bonds forming, I want to know how does the thermodynamics play a part and how does the entropy play a part? Is it possible you could have an exothermic reaction that becomes more ordered? It's possible. The question is that favorable or not? And we have to figure that out. And that's what? It depends. That depends. Because ordered is not, becoming more ordered is not a favorable thing. Remember, it likes to go to disorder. So disorder is favorable, and exothermic is favorable. So if you have an exothermic reaction that's disordered, it's always favorable. Which means if I mix them, it will react. No matter what. I don't need to add anything, I don't need to do any fun stuff to it, it will react. Okay, and we'll talk about this. He came up with an equation that took the two things that are important for discovering favorability. Isn't this going to tell us exo or endo? No. And isn't this going to tell us order or disorder? Okay? So, he put an equation together that puts both those factors in. Okay? Because if this is exo, we know that it's negative, right? And if this is more disordered, it's probably going to be a positive change in S, correct? And we said those are the two things that make it favorable. But what's the sign of G going to be if you have a negative change in H and a positive change in S? It will be negative. So, if we do a Gibbs equation and we get a negative change in G, whoops, we know that the reaction is favorable. Okay? Let me show you the opposite. So this was my H minus T change in S. What does endo mean? Positive sign, right? Okay? Is that favorable from an energy standpoint? No. Okay? What if I'm becoming more ordered? What's the sign going to be? Negative. A negative becomes a positive. What will your G be? What sign? Positive. Does that make sense? From a mathematical standpoint, positive change in G, not favorable. Well, what if you have one of each? Like this is favorable, but this isn't. Or this is favorable, but this isn't. How do you know? Well, it depends on which one is more unfavorable than the other. Just like we said when we're doing chemical reactions, we always have bonds breaking and bonds forming, right? So how do we know if it's exo or endo? By the overall change, right? Which one is more? Same thing here, which is what we'll see as we do this. So there are two ways to do it. One's easy, one's hard. We're going to do the hard one.
Oh.
Okay.
Because the hard one requires us to do some of the other things we needed for this chapter. Okay? Here's the hard method. Using this equation. Why do you think this is hard? Why do you think that's going to be harder?
It just incorporates more.
Yeah, well, I have to figure out this. And we just said that takes looking in the book, doing our products minus reactants, correct? And then we also had to do that for this, correct? And are the units for these two the same? So we got to probably manipulate some units as well, don't we? Okay? And guess what this one is?
Oh, nice.
You remember that third slot in our look at your chart. What's your third slot? In your G. So we could just do products minus reactants, be done. In this one, we have to do products minus reactants, change the units, then we're done. But the reason why we're going to do this one is because we have to do the other things that we've been talking about this chapter. So, yeah. Ready? It'll be fun. Don't worry. Okay, I want to see what you have in your notes. I don't want to MGOH. Okay, perfect. Let's do this guy. Now, if we have time, I will show you the second method. Should give you the same answer as the first method, but we are going to do this, and this is probably the only one we'll get to. The next one is the exact same process, and I think you guys will get it after the first exam. Okay, if I want to find the change in G, I've got to first find this and this, correct?
Right.
Okay, which one do you want to do first?
Change in H.
Okay, let's find the change in H for this reaction. What would I do?
G back.
You would subtract your, you would find all the enthalpy values
Add the-
from the chart and then subtract the.
Okay, we did this. All of you were here for this, right?
Yeah.
Okay? All of you were here for finding the change in H. Products minus reactants from the book. So let's do it. Okay? Products are here. Notice how it's 1 mole of each. So I'm going to save time by not even, well, no, I'm not. I'm just going to put it in. I don't want to make that quick assumption. Okay? Can somebody find the enthalpy value of that? Can I get 2 people so it's confirmed?
It's going to be negative 601.6.
Yep. Marty.
Make
You
sense?
said 2 people, not 3.
So why'd you answer third?
Okay, be quiet. We don't have time to waste. Okay? I have 1 mole of H2O. Make sure it's liquid H2O.
Negative 285.8.
Do I have, oops,
That's true.
is that correct?
Yes.
All right, there's my products minus my reactant. 1 mole of this. Negative what?
924.5.
Do I have a second on that? Okay, solve for it. Everybody understand where we're getting these numbers, why we're plugging it in the way we're plugging it in to find our change in H?
Yeah.
We have 37.1. Does anybody have a second to that number?
I have a second to that.
Okay, what is it? 31 point,
37.
37.1.
37.1. What are the units?
That would be
Joules.
kilojoule.
Kilojoules.
Ah.
Okay, the moles cancel. Did everybody get that? I actually don't even have an answer key for this one.
I think we can
Reverend, you got a third on that number?
I do.
Okay? Now, let's stop and think. We know that doesn't only depend upon the energy, but from an energy standpoint, is this a favorable energy?
I don't
What did I say was favorable versus unfavorable for energy?
know.
It's not favorable.
It's not favorable. Why not?
Because it's positive.
Because it's endothermic. But that's not the only piece of the puzzle here, right? Let's find if it becomes more ordered or more disordered. Change in S. Correct? Same process, different numbers. Yeah? Product, find the entropy of MgO.
27.
27.
Yep.
Joules per mole Kelvin. What our second product?
Negative 285.8.
I'm going too fast. Everybody good so far?
Where did she get that number?
Is that not the right number? That is the enthalpy number, isn't it? 69 point what? I was gonna say that seemed like a whole lot of order there for liquid H2O. I have a second on that, correct? That one's the right number now?
Good.
Okay.
60.
Amen on that?
Equals
33.79? 33.75? Do I have a second? How do you even go?
I'm not.
Not a big deal.
I second that motion.
Now, is this a favorable entropy based on Newton or not Newton, the second law of thermodynamics? What does a positive change in S tell you?
Means there is more
Disorder. That is favorable.
Oh, that's right.
We go from order to disorder.
Nice.
So we have two conflicting things here, don't we?
So it's going to be a negative.
It's, yeah, it's not going to be favorable.
We'll see. You remember, right? Okay. But remember, these are different units, so we'll see.
Wait, so there's more not favorable than there is favorable.
But they're not exactly the same units, and there's a temperature
Oh.
difference.
Oh, we divide the kilojoules by Kelvin, and then we have to convert kilojoules to
Okay,
kilojoules.
so we have the stuff we need. We need to manipulate some units here. Okay, the question is, do we want to convert joules to kilojoules or kilojoules to joules? Doesn't matter which way you do
Joules
it.
to kilojoules.
Are we cool with going joules to kilojoules? Alright?
Yeah.
Is that alright?
Sure.
Now I could set up a conversion factor, but it is moving 3 decimal spots to the left. There's our new number. And I'm going to change this to kilojoules per Kelvin. Everybody see it so far? Let's plug in our change in G. Okay. 37.1 minus, what's my temperature?
372.
298 Kelvin.
Why is it not 2?
Because it's standard state.
It's in.
Okay. Times what?
Your change of S, which is favorable.
You see how my Kelvin is going to cancel out? And then I'm going to be adding my kilojoules. Okay? Let's solve. My guess is it isn't going to be favorable, but we'll see. And isn't that what you guys said?
Yeah.
Do I have a second to that?
Yep.
Now, Kelvin cancels. You're adding like units, so it's just kilojoules. So, we have found the Gibbs free energy. Is it favorable or unfavorable from the sign of change in G? What did we say?
Negative is favorable, so it's not favorable.
Not favorable. Now, before you leave, I want to make this very clear. A favorability of a reaction didn't just depend on one of the two. It depended on both. So here we had one that wasn't favorable and one that was. And so in order to know if the overall reaction was favorable was dependent upon which one was more unfavorable or favorable. Okay? Now, we didn't generally get to the next problem, but it's the same type of problem. Okay? Could you solve this product minus reactants using the G values in your book? You should get the same answer as that. Okay? Should be equipped to do all right on your homework. If you have any questions, come see me.
Did you get the
But
Oh, we need to fix this. Oh, I took it off. I'm telling you, you need to get number 2. Old people. I'd rather, that's what I. Only.
I still want
And
to.
quad. Oh, that's the same. Because is it gold?
I thought you were lying
Is it gold? Is it gold?
I know, I was gonna say.
were you not wanting to turn it in now?
No, I knew I needed to. I just wanted
$3 drawstring bags, anyone?
Well, I kind of have told people the answer.
Oh, that's fine.
I almost got some freshmen.
What?
Really?
What? Wait, what?
I'm not picking on
You
them.
almost got
They wanted a
some
drawstring
freshmen?
bag. $3.
That's oh, I saw.
I have permission.
Who's back?
Nyla.
I'm assuming you don't, so on Friday, we just went over that worksheet.
Oh, okay.
And then yesterday, we just did 13B part 1, which most of that was reviewed anyways. So if you by any chance do any of the homework outside of that one?
Physics.
Alright, so what we got going on here? This belongs into this ratchet that hits this ratchet, that hits this one, then this one, then this one. Then this one, which is that, and then that drops down.
Yep.
And that pulls this up.
Well, this is gonna be like.
Oh, no!
No, it doesn't. It's alright. So yeah, the ball
I didn't do.
is on the top of it, and it's down like that.
It's not due
And then when this drops from the,
You get 3
when this
days,
drops
you're
from the
done.
trapdoor, it like pulls it down.